All right, so let's actually explore implementing stopping rules and pruning in R. It turns out this is not so bad. So the first thing we need to do is define some stopping rules. This is done with the, and I'll be consistent here. This is done with the rpart.control mechanism. And notice that you can't really see it here because it's just so small, but it already pops up what these values are: min split, min bucket, and CP. So for instance, if I say min split equals 20, min bucket equals 10, and CP equals 0. That's one set of stopping rules. It's slightly more permissive. It's easier to split using those rules than it is using the default rules. And we can actually make our model. So we'll say model equals. And in fact, we can just say basically what we said earlier: competitive as a function of everything, data equals training. And now all I need to say is control equals stopping rules. Okay, so this is how I say to use these stopping rules. If you don't put this here, it uses default stopping rules, which are like 27 and 0.001 or something like this. It's a little bit more complicated. So we can build this thing. Oh, I didn't run that. Our part dot plot model. You can see maybe this thing is slightly bigger. Not a good sign. Well, it is a good sign. This stop thing, see? It's like, oh, I'm thinking. Oof. Okay, so this means if you see this thing, this warning, it means that it's trying to plot in the space that you gave it, but it's not sufficient. So this model is significantly bigger, right? Significantly bigger, and perhaps overfit. You could make it even bigger if we went down to 2 and 1. These are kind of the most permissive stopping rules. We'll just leave it where they are. So just be careful with plotting. Sometimes like just trying to plot will ruin the whole thing. Like it just won't be able to plot. It's just too big. So you don't always have to plot when you make your overfit tree. So this tree is likely overfit with these easy stopping rules. And then what we want to do then is bring this thing back into a some kind of semblance of normalcy. So in fact, let's just do this real quick. I just want to check. I'm gonna copy and paste this. Observations stay the same. I just want to see. So here's what I've done. I've made my tree, my overfit tree. I'm going to make some predictions, and then I'm going to compare those predictions to the observations and see what happens. I actually don't know. So the overfit is actually slightly lower than the default, which is interesting. So it means that the default wasn't very good. The default stopping rules weren't very good. And it's also saying, ooh, maybe we can actually do better. Like maybe we can actually improve on this. So sometimes what you'll see is that the overfit error rate will be worse than the original tree. But what it's saying is it's kind of tough to know. We have to play around with the stopping rules to know whether the default ones were any good. It's kind of difficult to know beforehand. So what we do now is prune this tree. And what we're going to do that with is this easy prune function here. So this is something that we've written for you. So if we say easy prune and then we feed in the model, this is going to prune that model back to the right size. And by that we mean take off all the unnecessary branches and hopefully make the model of the right size. And so if I just go through here and change all my suffixes to pruned, I can change this one to pruned, and this one to pruned. So I've built my model, overfit, I prune that model, and then I make predictions using model. Okay, yep, that's fine. So I overwrote the old model, make our predictions, make the predictions with the pruned, and then compute the error rates. Let's give this a shot. See how it goes. So my face is in the way. So notice what happened. This is a good thing. So by using the default stopping rules in R, this was the very beginning. Let me make this slightly bigger too. All the way at the beginning, when we computed the error rate with the default stopping rules, we had an error rate of 30%. This is not super great, but we don't know whether we can do that much better or not because it's just kind of a shot in the dark. So instead what we do is we build a massively overfit tree, like way, way, way too big, and we compute its error rate. That error rate was 28%, which is just kind of, okay, that's 28%. But now when we take that massively overfit tree and we cut it back and we reduce the number of bad splits, hopefully that error rate is going to decrease a little bit. Even if it doesn't decrease all that much, it's a much simpler model. So we have a much simpler model achieving about the same performance, which is itself really good. But in this case, we actually saw a slight performance increase as well. Notice that like overall, like we've gone from 44 to 27, which is, not inconsiderable. Again, this is going to kind of depend from time to time on how this, how your data set looks. Another thing to think about is like if we run this over and over again with different training and test partitions, what happens? So in this case, the pruned is still the best. I just reran the whole thing and rerun the whole thing again. Pruned is still the best. Rerun the whole thing again. In this case, the pruning actually like increased the error rate a little bit. This can happen too. Like you've made a much smaller tree. Maybe you pruned back too far. We run this again. It's kind of a similar situation. Now they're the same. So there is variability. It's not like it's constant. But the idea is that we can have a massively smaller tree that either does better than the big tree or the same as the big tree. And in both cases, we have a win. We've either decreased model complexity, made a more efficient model, and maybe we've gone on to actually have better performance. But the key to all of these things is defining the stopping rules and then pruning the model back to the right size. And when I say defining the stopping rules, I mean for a very overfit tree. So making these things very, very permissive. So in fact, like we could go all the way down to like min split 2, min bucket 1, CP 0, this type of thing. But I encourage you to play around, like different training test partitions, try plotting things with different min split and min bucket. Just be careful not to make them too small or the tree won't plot very well. Like gain some experience. There's nothing better than just kind of trying different things and seeing what happens to these numbers to get some intuition about how these things should be structured.